Sciences, member of the American Academy of Arts and Sciences, a member of the Hungarian Academy of Sciences, a recipient of the Gödel Prize, a Packard Fellowship, the John von Neumann Medal, the Dantzig Prize, and the Fulkerson Prize. So thank you for honoring us. This is for you.
Oh, thank you.
And maybe.
Well, I guess oh, they're showing. Oh, I should put it on.
Yes.
Okay, well, thank you very much, and I can repeat the request that it would be lovely to have most of you close by. This is a ginormous room. Oh, you can't hear me. That's unfortunate. Okay, is that better? Excellent. So, this is a great agenda, and I think there's a lot of potential in both direction of machine learning getting used or understood better in how it works in games and what it does in a game environment, and also that is machine learning contributing to game theory, and also the other way around, that game theory contributing to machine learning. In all honesty, my talk is more the first part of this agenda. That is, I want to better understand what happens in games if multiple learners interact with each other. So that's sort of the topic of what I'm talking about. And I guess the kind of games I like, or maybe my favorite one of these games, is traffic routing or package routing, which is the kind of game that you would play over and over again. It's a game. If I drive or route my packet, that causes congestion for others. So clearly it's a game. The people are interacting with each other. But at the same time, it's really ideally set up for learning, in contrast to games that you play once and you do a lot of preparation. No one's spending a lot of effort on figuring where to pen this one packet or this one time driving. Rather, experimenting and learning from the past is a natural state. And I guess the thing that at least the results I'm going to tell you about is focusing on is a feature of this, which I think is very important to make it more realistic, is that while it's the same game, that is, we're writing packets every day and the network is not regularly changing, the traffic does change. That is, there are some changes in where the traffic is going, maybe based on the time of the day or other random events. And what I would like to get, or at least they're one of the things that we actually know how to get, is that over the many previous years, maybe starting close to 20 years ago, there was a lot of beautiful results on understanding that Nash equilibrium in many setups is really results in high quality or reasonably high quality solution. I guess one example of this, and I guess this is what our Gödel Prize was for, is a price of energy in a congestion game modeling the traffic delays that are happening here, where we proved that if the network is capable of accommodating twice as much traffic as what you have, then a Nash equilibrium will have not that bad a solution. In particular, maybe the bus phrase price of energy has been used for this cost of a Nash equilibrium compared to the cost of the social optimal solution, which is, in some games or many games, it's reasonably good. And since this around turn of the century, there have been 1 million papers, and I'm citing here not 1 million, but many of them, which proves this kind of bands that, if players settle in Nash equilibrium in a certain game, then that's not optimal or might not be optimal, but it's not very far off from the optimum. We're not very far in all of these examples here, a reasonably small constant factor off. Okay, given the introduction, I don't have to convince anyone that Nash equilibrium as a notion has troubles. And I guess one of the many troubles is that there might be many Nash equilibria, that players need to know who are all the other players and what are they doing. And then maybe last but not least, there's a computational difficulty of finding it. So that's not a really viable notion of understanding things. And I guess in this application, whether it's traffic routing or adductions, we're playing it over and over again. And I guess can learn from the data. So repeated games is a natural model here to model what's going on. And I'm going to use a very theoretician's, very simplistic model of a repeated game. Time goes in time slots. And every time slot, every player does something. Some outcome happens. And they repeat this. The players hopefully are aiming to average, optimize the average welfare or average cost, or minimize the average cost or maximize the average value. And a very important assumption that at least the game theory perspective has trouble getting away from, these players just want to optimize their own welfare. They do not aim to hurt any other player. So the right model here is traffic routing. You just want to get home. You not actually want other people to take a long time on the road. I think that's a reasonable model for this particular application. And we're asking what can we say about the outcome. In particular, how stable does they have the system to be before they can settle in something reasonable. So for this purpose, this direction has started a long time ago. And I guess the maybe first paper in this direction is Julia Robinson's from early 50s, where she proposed fictitious play as a form of pre-play for finding a Nash equilibrium. That's still a direction that's going on today, trying to understand what does it take to, what kind of playing would it take to find a Nash equilibrium. And there's some positive examples, but they're kind of rare. So finding Nash equilibrium here will mean something of the sort that the picture aims to suggest over there. They do something for many iterations, and eventually they either settle on a Nash equilibrium or approach a Nash equilibrium in the limit. There are a couple of nice results. Some of them, like my paper on the bottom from now 10 years ago, is even trying to say that what they settle on is actually a decent Nash equilibrium, not the worst kind, but something better. These are all very beautiful and important directions that even happening today. But that's not what I want to talk about today, because as a high level, in almost all games, it's not going to work. Instead, I want to think of Nash equilibrium as with two words. Nash equilibrium in this setting is a stable outcome that's also in a sense that's stable and has the no regret property. And this is the classical Nash equilibrium property. That is that every player plays some sort of action. So A is the vector of actions here. And for all players I, the cost if they were to switch to a different action X is greater or equal than whatever they're getting. That is, they do have no incentive to deviate. This is what is classically called no regret. And the change of focus would be that suppose everyone plays a no regret strategy, so everyone achieves this no regret without ever stabilizing. What can we say about the outcome? So with the interest in this workshop on deep learning, let me actually start by why I like no regret learning as my behavioral model. And maybe before even I say that, let me actually say what I mean by a behavioral model. So what I certainly do not mean is, I don't know what's your favorite no regret learning algorithm, but say it's multiplicative weight. I'm not proposing that if you're a driver, then you should from now on please choose your route using multiplicative weight. I can explain to you why that would be a dumb move, and please don't do that. I also am not proposing to use any other named algorithm. What I'm proposing instead is that whatever you do, which might be deep learning, appears to satisfy the no regret property. And I would love to actually have a better theory of understanding what deep learning algorithms do or don't satisfy this property. As a behavioral assumption, it's super appetizing. It simply says, and that's the first line down there, if there is a consistently good strategy, please notice it. In fact, I'm hoping that doing better learning algorithms, other than the ones that really aiming to satisfy this property, you can do better than that. No regret is not an unbeatable strategy, especially not in the kind of environments I like here, which are somewhat changing. A proper learner should be able to adjust to the environment. Doing better than the single best strategy with hindsight is ample possible, and they should be able to do this. Doing worse than a single strategy with hindsight, that's kind of painful. Please don't do that badly. So that's what I mean by a behavioral assumption. Behavioral assumption does not mean that I name the algorithm that people are using. Instead, it means that I'm hoping that whatever they did satisfied this mathematical equation. That is the no regret property. And I actually made a weak version of the no regret property. I just said that the regret is little O of the time. That is not particularly the best learning algorithm, but at least something going to 0 as time goes to infinity. I do admit the bold-faced line in the beginning. I'm a theoretician. I like proving theorems. And this property is beautiful because I can use it. And in fact, so there are multiple very nice papers. This direction started with Avrum Blum and 2 of his collaborators, suggesting this as a behavioral model on traffic routing. And since then, there were a sequence of papers basically proving that all of those results that I showed you for price of energy actually extend, assuming the payers are no regret learners. And let me repeat again, I'm not assuming they're doing multiplicative weight. I'm not assuming they do follow the perturb leader or any of the name algorithms might know. Instead, I'm assuming they're doing something that happens to have this property. I don't care what it is. There are some behavioral evidence that this might actually be a reasonable assumption, and I cited here the papers, but will just vaguely mention 2 kinds of them. Some of them are human subject experiments, so that's true on the Orley Erev Ross 86 paper. Fidenberg Perjakovic also is an experimental paper, and Nissan and Nati from DubDubDub17 is also a human subject experiment paper. They vary in what exactly the high-level message is, but roughly speaking, they all support that human players do actually satisfy the no regret property. That is, given enough evidence, if there's a really good strategy with hindsight, they do wake up to this. And then some of them, which is 2 of my papers with Denis Nekipelov, are actually based on automatic learners. That is, the first one up there is Microsoft Bing Data for adductions, and the last on the bottom is Zillow Ad Data, where the Zillow advertisers are the real estate agents. And again, roughly speaking, what we're saying that these learners actually using learning algorithms, so not very surprisingly, they do satisfy it, even though I have enough evidence to know that they're not doing these named learning algorithms. They're doing something of the gradient descent style, but they do satisfy the property. So why do I like this? Actually, before I go in what one can say with this property, I thought I add a slide to give you, as in the spirit of this being a workshop, in cool directions that I think some of us are currently pursuing, and maybe I can induce many of you to pursue also, of what is it that I would like to do better, that is limitations of no regret as a learning assumption. So one problem that in some setups, for example, in multi-unit auctions, no regret learning is too much. There's so many options that achieving this property is computationally hard. Even when learning is actually a viable property, literally running these no regret algorithms, especially running multiplicative weight or follow the perturb leader or any of these algorithms, is exceptionally dumb. And I guess there are 2 papers in this direction. One won a form of a best paper award at EC last year, and one is a paper from the current NeurIPS is trying to say that if you're a seller and you know that your buyer is running a low-regret algorithm, you can extract all the profit from them, because these particular ones, and not just multiplicative weight, but anything on average based, is really painfully dumb at this. So you have to be careful of what exactly you're doing. And maybe more interestingly, why should I be able to expect more from learners? So one direction I already hinted at, and that's what the results I'm going to tell you a little bit about is that learners should be able to adjust to changing environments. That is what in English you would say learning is good for, compared to a Nash equilibrium. If things change, a learner would notice it and adjust. And maybe different versions of regret can do better here. There is something dumb in using any form of learning algorithm, which the counter-positive you're thinking about is how much money you would have made had you changed your strategy and the opponent didn't. This is a game. If you change your strategy, the opponent will change it too. I know that. So there are notions of learning that seems to take into account this. There's an early for the Farias-Megiddo paper from now 16 years ago, and a more recent notion of policy regret that's going in this direction. And then and all of these, both of these somehow want to take into account that this is a repeated game, and you don't actually want to make a lot of money every single second. You want to make a lot of money on average. These are sort of cool directions, some of which I'm pursuing and some of which I'm not, but I'm hoping that many of you will want to do that. Let me tell you a little bit about what kind of things we can or cannot prove. So I guess I started by defining this price of energy notion from Kotsopios and Propodimitriou. So in terms of routing, where you're minimizing the time it takes for all the packets to get to their destination, there's a cost that is the average time. And you want to compare that to the optimal cost. I mentioned that Avrum Blum and the sequence of papers culminating in a beautiful summary paper of Tim Ravgarden extend this to no-regret learning outcomes. One sufficient, and that is sum of the cost of the players over the times compared to t times the optimum if you played for t periods, because the game isn't changing, so the optimum isn't changing. So there are t iterations here. And I want to tell you a little bit about that. The very same machinery, or at least similar machinery, allowed us to extend it to a situation that's much more realistic, where it's not only that the people are learning, but I'm going to change the game. And in particular, the way we change the game is the packet routing variation on this. That is, when the packet streams are changing as we go. The particular model we like using is that every iteration, every player vanishes with some small probability, and a worst case new player shows up. In a population of some capital N players, their expectation NP players will change. I like this model in particular because it necessitates learning. With the worst case, there is nothing the players can do to predict the future, and they're just going to have to watch what's happening and be able to adjust as the changes are happening. If players stay long enough, our results show that similar results show to the learning outcomes. I guess, let me give you a very, very high-level 2-second overview of what takes to prove such a result, and then maybe, I don't know how many minutes I have. I have a lot of minutes. Okay, then maybe, that's beautiful. So then I can give you a little bit longer overview of so what does it take to prove such results? So I guess one summary statement that's worth remembering is that all of our price of energy proofs, including the ones that I mentioned, every single one of them that I mentioned in the previous slide, and almost every single one of them that we have, works in a following very, very simple way. you think of an optimal solution, that is a solution where everyone writes in a way that some central designer told them to go, and I'm going to call this as a AI star. Star here just refers to that's a centralized optimum. In a centralized optimum, in a Nash equilibrium, no one wants to deviate and do something other than what they're doing, and in particular, they don't want to do that optimal thing. The single inequality I'm using is the one that's written out here, is that the cost of a player is no worse than the cost of the centralized optimum. And then in this class of games, there is a inequality that Tim named smoothness inequality, which looks a little magical as you first look at it, but maybe I can give you a 10-second or longer than 10-second sort of feel of, this is an inequality where your feeling should be that, oh yeah, if this is true, then clearly this is a good game for players. What this inequality says is that for any part, the way to read this inequality is I look at a particular game situation they're in, so I say a vector A of actions they're taking, and I want to compare the cost of each of them deviating to the optimal strategy on average. And what this really says, that if the current solution is super painfully bad, that is, the current solution is costing insanely more than the optimum, then some player will want to deviate. Okay, that depends how big lambda and mu are, but if optimum is much, much, much cheaper than the current cost, and in this inequality, I want that mu is less than 1, so that this lambda times optimum is a small addition compared to the current cost, then one of the players is better off if they're switching to the optimum. This naturally means that there is a price of energy band, because indeed, then we can compare this deviation that they all don't want to do to the current solution, rearrange the inequality, and get a band on the price of energy. And indeed, this is a tight band in all the games on the early slide. So what Tim noticed is that this is not only a nice and very general proof scheme, but also a proof scheme that's actually set up for no-regret learners. The very same thing works even if they don't reach any Nash equilibrium, they just have the no-regret property. And the version I wrote out here is the one I actually better like as a behavior model, what we like calling approximate regret. Instead of insisting that you literally compare that to the optimum, I give you a fudge parameter epsilon, and the epsilon I like thinking of is 5% or something like that. And that you're within 5% of what you could have done otherwise. And you do the same rearranging of inequalities, simply observing that back there, I didn't actually use the Nash property, I simply used the no-regret condition. And you get a convergence result, and it in fact says that any no-regret learner, if they satisfy this approximate no-regret property, then in converging to a high social welfare at a rate of 1/t, that is very fast as time goes on. Okay, that's the sort of classical result at this point, and what I want to get back to is this changing population, and changing population is every iteration, again, remember that was the model, every iteration, every player vanishes with some probability and gets replaced with an arbitrary other player. So again, these people want to learn from data, and I have to admit, in this changing population, this doing well compared to a single strategy with hindsight is rather weak, and honestly too weak to get anything out of this. It's easy to convince you that it's weak, like just think about, say, a setup with this red player on the picture, shows up, and as he shows up, there's a lot of traffic on the upper rod, and so he's going to choose the lower rod because that's the right thing for him to do. Remember, my replacement is a bit worst case, so maybe after a while this guy will vanish from here, and because the replacement is worst case, every single one of them will become another person that's instead writing on the bottom. We'll have to write on the bottom with no other choice. And indeed, in this case, the red learner, if he wants to get anywhere, he has to learn to adjust and actually change his route. Now, no-regret learning actually is good at this, and all you have to do is put in something I actually personally like anyhow, named recency bias. If you put the classical learning algorithm, add to it a bit of recency bias, then what you get is a learning algorithm that adjusts to a changing sequence of optimizers. So the particular statement that I want to use here, and maybe that's familiar for almost all of you, is a version where instead of comparing to a single optimum with hindsight or single strategy with hindsight, I compare to a strategy that changes k times where k is a parameter. And if it changes k times, the error will go up by a factor of k, but it's still actually for reasonably small k's, this is a bounded error. So something that learning with recency bias can do is adjust to a slowly changing sequence of comparators. Now, why do I like this? Because as my changing dynamic population game, the optimum will be also a changing animal, that is, the optimum changes. And what I really want to do to adopt the previous proof strategy is have an inequality of the kind I wrote up there. That is, when I compare your cost, your selfishly or learned strategy's cost, compared to the centrally designed optimum, where now the optimum is also indexed by time because it's changing as time goes on. This is a bit too much to ask for because the optimum is a super sensitive object. And here it is. The sensitive object in a one of the simplest games on life is, say, a matching game. Here is the optimal matching solution. And if I only have one person vanish, then suddenly optimal matching can have every one of the players switch, or via ginormous augmenting path switch. So it's hard to expect that such a changing object will be able to adjust the solution. But maybe just from what I said so far, most of you will feel like, oh yeah, that kind of thing should be true. If I were to have a comparator, an approximately optimal solution that's pretty stable, that rarely changes, then I could, learners could adjust and get that kind of solution close to this, what I call A tilde here. So instead of comparing to the true optimum, if I had a not-so-changing optimum, then that not-so-changing optimum could be learnable, or more precisely, could be learnable to do at least as well as that one. And indeed, that's what our results show, that if there is an approximately optimal solution that's pretty stable, then learning algorithms can learn to do at least as well, or more precisely, the recency biased version of a no regret as a behavioral assumption allows us to prove that it has the good price of energy. And then maybe as a final point, which is really a pure optimization problem, in many games, we do actually have not very hard to prove that close to optimal stable solutions do exist. To formalize the results, we actually prove the price of energy band has 3 parameters. This technique will not allow me to go beyond what was the price of energy band. There's a little bit of extra loss due to the regret error. And finally, there's a further, again, usually small extra loss by how much I lost, because I'm not comparing to the true optimum, but rather to such a stable optimum. But in each of these, as the changeover vanishes or goes to 0, probability goes to 0, or the game gets pretty large, these parameters goes to actually proving true optimality. Maybe rather than telling you anything about how these approximation algorithms, how the approximately optimal solutions work, I want to spend my last couple of minutes on trying to reiterate what was good about what I tried to what we can prove and what is it that I would love to be better at. So on a positive side, I do think learning, whether you're doing any form of learning, is an excellent way to adapt to the opponent, excellent way to adapt to changing environment, and it has the beauty in games that no need for common prior. It doesn't have to be that we all agreed that we know who the players are and what usually is supposed to happen in this game. You can just start playing and learning. This is excellent in any game where experimenting is not too painful. Package routing and adductions are maybe the two killer applications here. But there are many others where individual game playing is cheap enough that you can afford to learn from the experiment in the, or from the experience in the game. What we did prove, and that learning players can do well in dynamic environment, and approximate if in most of these games, almost all of these games, we get a price of energy band where we're losing a teeny bit of extra compared to what the price of energy band is. There are many, many open questions here, and I guess I would like to, I'm personally actively still working on this, and I hope many of you can be convinced to also consider working on this. I guess one direction that maybe is more clear from what I was talking about is that one can hope that learning can do better. And I guess some things that I did or didn't mention, I think some games, the worst possible price of energy is an incredibly silly, coordinated, unfortunate outcome. One would think that learners don't find that stupidity. That is, they're going to do better than finding the worst possible Nash. I'm not hoping that they find the best possible Nash every single time, but hopefully they can do avoiding the particularly unfortunate bad ones. Maybe a more general direction is that regret is not quite the right notion here, and not thinking of how the opponent will react to my strategy changes maybe simplistic, and policy regret maybe allows us to do what I wanted to do in the first place, get better outcomes. We definitely need to work to avoid figure out what to do in cases where learning is too hard. And maybe last but not least of these bullets is any result I currently have is about social welfare. That is, how well collectively do as a society. Individual players want to do well individually, and I want to prove that if you're doing a decent learning algorithm, or what should be the learning algorithm you should be doing, so that your welfare is high compared to other kind of welfare you could have had. Social welfare is nice, but this is not a recipe to convince players to do this because they want to optimize their own welfare and not society's welfare. And then maybe a different and also very active direction is there is a limitation in the repeated games I have been talking about, where I basically assumed that there is no leftover between iterations. So for example, if I think of car traffic routing, and this is the morning rush hour, then indeed it's a reasonable assumption that no matter how bad traffic was Monday morning, by Tuesday morning those cars are gone, and they're not jamming up the highways. But if I'm thinking of package routing, and this is the second by second or millisecond by millisecond iteration count, then this assumption is not valid. If in a millisecond there was a lot of packets waiting to be transmitted, then a millisecond later there will be all those packets still waiting there. So there's carryover effect. This is true on ad auctions, where the carryover effect is money. That is, when you win auctions, you deplete your budget. When you lose them, you have more money left. And it's true in packet routing, and this, again, is a very active direction with a lot of us working on this. And again, both the question of what will happen in a game if people are learning, and what is the right learning algorithm to do in these games are both super interesting. And thank you very much.
No. Can you hear me? Okay. So thank you for your talk.
We can take a couple of questions. There's a mic over there for anyone who might want to direct a question to the speaker. You have a question?
Yeah, I have a question if nobody else has a question. So I was wondering, like, when you have these no-regret algorithm, like how to relate these convergence results with the optimization convergence result that we have with smooth games. Because here you're looking at the regret of each player compared to their fixed action best thing they could do. And so you have multiple costs, I guess, because you have multiple players. And so now how do you relate all these kind of regret aspect with, I guess, your little O of t with convergence to a point or some kind of like gap or the notion we have in optimization? I don't know if you have this
right. So there are two questions, two ways to think about your question. One is in some games, such as package routing, they do actually converge to a Nash. So then I can literally answer your question because there is a convergence there, and how fast are they converging? And in fact, the best point convergence results is coming out of the regret band. So you just have to add up the regret bands. If I think about price of energy, rather than thinking about point convergence, then I guess I'm going to lose a constant factor, right? The price of energy will be like, 4/3 or 2 or some other small number. And in that case, I'm very tempted to, if you cared about price of energy, whether it's 2 or 2.1 or 2.01, probably you don't care. Or more precisely, if you really find 2.01 painful, you probably also found 2 painful, and you don't care about this whole direction. In which case, I want to go for approximate notion of regret, rather than this 1 plus epsilon, rather than the true form of regret, because I'm going to lose a constant anyhow, so who cares about the plus epsilon? In which case, I can put the regret error really, really low. And that's what drives the better convergence results. They're not converging to a point at this point, this speed. They're converging to a convex set at this speed, the convex set of reasonably good solutions. And this is more general than games where you actually do converge to a Nash. So other games, such as, for example, adductions, learning does not converge to a Nash. They converge to a set of all correlated equilibria. That's a convex set. It's bigger than Nash's, and we converge to that at a much higher speed than the point convergence. But if I insist on point convergence, again, I have to rely on the results you have, and then it's 1/√t style convergence. The reason I'm getting better because I'm willing to converge to a bigger set.
Thank you. Oh, we have one question. Yes.
Yes. Applying these notions to deep learning settings, two things come to me. First of all, we're almost surely going to want approximate convergence because you're never going to have a perfect GAN. The notion of equilibrium there is very hard, but you want it close enough to a good solution that you're satisfied. The other is a term that I don't think I heard you mention, but is clearly part of the literature, which is mechanism design, which is that we are the god of GANs, or we can set things up however we want. Our learners are not fully strategic, but we can have them learn however we want them to learn from their own play, from each other's play, from past payoffs, whatever, because we want the system as a whole to get to equilibrium as reliably and quickly as possible.
So I guess really this is two questions here rather than one, at least the way I look at it. Yeah. So one question is the deep learning. How does deep learning, using deep learning, you want something approximate and not exact because the exact one is hard to reach. I'm completely on board with this. I love approximate no regret, and I think that's, at least for games, that is the right notion. Definitely changing games, that's the right notion. Who has time to find the true optimum? Life is too changeable to find the true optimum. What I would love to be able to do, and I hope it's actually true, but I can't prove it right now, is that these deep learning algorithms, in some sense, will reach an approximate no regret property. They will do better than no regret, not worse than no regret. Again, the notion that if there's a really good strategy, please wake up and notice it, is so painful that I hope any decent learning algorithm will actually achieve this property. That's one. The second, the mechanism design, there's definitely a great question in mechanism design. I guess at least the work I'm talking about is about preset mechanism. And in some way, the GAN setup is maybe not even a game, because the game is something we're using as a way to find the right solution, rather than there are actually players who have actual interest. But mechanism design is a feature even in regular games. Like even in the package routing version, I could say that, hey, I did design it. I'm going to, on this place, I'm going to put in a really bad router because I want only 2 people to use it who desperately need to be here. And everyone else, I want them to avoid it. So let's put in here a slow router. That's mechanism design. I still, at least the way I'm thinking, because I'm more a game theorist than a learning person, is want to think about games where there are true incentives, and I can't change the incentives. I can change the mechanism, maybe.
Thank you.
Thank you. And before I ask the last question, I'd like the spotlight presenters to get closer to the stage. David, Eric, Olia, Yan, Wojan, etc. The schedule is on the website. Please check. We have 10 spotlight presenters. Come closer. So my last question is, we worry about stochasticity sometimes in those learning problems. And it's sometimes hard to tell whether the reason we're not converging, which might be good or bad, or it's not clear, it could be either the actual dynamics of the game itself, or it could be the variance from the stochasticity in our gradient oracles, etc. So the results that you showed us, or the results that you focus on, do they involve stochasticity as a component?
I guess I'm not sure I understood which stochasticity you refer to. So there is stochasticity on the game players playing, because they're using maybe a randomized algorithm. There is stochasticity in their behavior, and the answer to that is yes. We can still prove stuff with that.
Right.
There is a second stochasticity, which I'm not actually in the models, but it could be, probably should be, you're right, is that the environment, like there's some random environmental effect, not the games, but occasionally some things don't work or go down or whatever that is. The environment itself is changing in a stochastic manner. And that's not at the moment in our model. And then, in fact, it's one of the active directions in looking at data is trying to understand, for example, on Microsoft Big Data, how stochastic is that environment, and is their ability to get truly no regret is because they don't want to, they don't pay enough attention, or is it because the environment's too stochastic and too changing, and they need to adjust to the changing environment. So it's a great question of where the effect really lies.
Thank you. Let's thank the speaker once more. And now I'm going to call the spotlight